So, kites. What makes a kite a kite? Okay. So, a kite is, actually, let me see, I think it's defined. Okay. So it's actually defined back on the previous page. I apologize there. So on page 471, a kite is defined as a quadrilateral with two distinct pairs of congruent consecutive sides. So this is different than like a parallelogram whose opposite sides are congruent. And a kite, you have two distinct pairs of congruent consecutive sides. So there's one pair of congruent consecutive sides, and there's a distinct second pair. Distinct means that they're not, this pair of side lengths will not be the same as this pair of side lengths. Okay, they'll be different. And it forms what we call a kite, right? It looks like a kite. Properties of kites. Okay, so if a quadrilateral is a kite, then its diagonals are perpendicular. Okay, and again, you kind of look at it and you're like, yeah, that makes sense. I can see that. If I drew the diagonals there, if I drew the diagonals there, they look perpendicular. If a quadrilateral is a kite, then exactly one pair of opposite angles are congruent. Only one pair of opposite angles are congruent, okay? And that's these two right here. In this case, the picture Q and S. They're the congruent opposite angles. Only one pair are. If you look here, P and R, very clearly not congruent, right? P is very much smaller than angle R is. However, there is a special relationship with P and R in this case, okay? One of the diagonals bisects the pair of non-congruent angles. So if these are the congruent angles, then this diagonal bisects, whoops, I just drew off my paper. This diagonal bisects these two angles. So notice here, this diagonal QS does not bisect angle Q or angle S, but PR does bisect angle P and angle R. And then, if a quadrilateral is a kite, then exactly one diagonal bisects the other. And again, you can kind of see that in the picture. It's like, well, duh, PR is clearly not bisected by QS. But QS is bisected by PR, right? It looks like, you know, Q to T there is the same as T to S. All right, so you can kind of just see it in the properties there. Okay? So let's hop over here, excuse me, and try these two problems that are given to us on the next page. So in this kite, ABCD, the measure of angle BAE is 32 degrees. So BAE, 32 degrees. And BCE is 62 degrees. Okay? Find each measure. So we're asked to find the measure of angle CBE. So that's this guy right there. Okay? So, ideas here. What could we maybe do to figure out what the measure of that angle CBE is? What can we say? Yeah, Hunter?
Can we say BEC is 9 degrees?
Can we say BEC is 9 degrees? Good question. What do you think? They look like 9 degrees, and in fact, if we go back to the previous page there, the very first property, right, is that the diagonals are perpendicular in a kite. So absolutely, we can say, I'm going to put the right angle over here because I don't have quite enough space, but yes. So, okay, if we say that BEC is 90 degrees, what can we then do?
We do 180 minus 90 minus 62.
Yeah, exactly. We have a triangle there, basically, so we can just do 180 minus 90 minus the 62 degree angle there. Okay. You get 28 degrees. So CBE must be 28 degrees. Okay. Great. All right, let's find the measure of angle ABE. So ABE, that's this one right here. Well, again, it's very similar, isn't it? So how can we solve this one? To find the measure of angle ABE there. What can we do? Yeah, Elizabeth? Yep, so we can again just solve. So the unknown angle there, we'll call that x. So she set up Elizabeth set up an equation, 32 degrees plus 90 degrees plus x equals 180. And then just subtract off the 90 and the 32, and we get x is 58. Okay. So there you go. Okay. Okay. Now, other properties here, right? So remember that this diagonal BD, right, it does not bisect angle B and angle D, but that means then the diagonal AC does bisect angle A and angle C. So if this angle is 32 degrees, that would make this one 32 degrees as well. And if this one is 62 degrees, that means this one would also be 62 as well, right there. Okay. So, yeah. All right. Number 4, if we look at the your turn, it's pretty straightforward. I'm not going to make you guys do this on your own. We can just do it together here. But the measure of angle ADC then in this kite up here. So ADC, ADC right there, this big angle. Okay. What's that one going to be? Let's go to, I'm going to pick somebody here. Let's go to, so Mason. What's ADC going to be? 86. How'd you get that? That's right, right? This angle is going to be 58 degrees as well. This one will be 28 degrees as well. And so, yes, 58 degrees plus 28 degrees equals 86. Okay. Yep, that's it. Okay? So that's kites. So, is a kite a parallelogram? Is a kite a parallelogram? Yeah, no, why not? So I want to explain why isn't a kite a parallelogram. Stephanie? That's one thing we can look at. Yep, opposite sides aren't congruent. Opposite angles aren't congruent. Well, one pair of opposite angles are congruent, but not both pairs. Are opposite sides parallel to each other? Yeah, it doesn't really look like it, does it? So, yeah. And so since a kite is not a parallelogram, can a kite ever be a rectangle? No. Can a kite ever be a square? Can a kite ever be a rhombus? Yeah, no. Kites are kind of unique quadrilaterals unto themselves, okay? So they don't really fit into that whole, kind of grouping that we had before. They're kind of separate, all right? They're kind of loners, but that's okay. We still like kites. Still have some fun things you can do. You can fly a kite, right? All right, so yeah, Ed?
Does the word kite, like the actual kite, come from the word of the geometric shape kite, or is it vice versa?
Right, which came first, the chicken or the egg?
Yeah.
That's a good question. I will Google that search after we look through here, okay? And I'll be happy to look, because I don't know. I don't know. That's very curious. I really couldn't say. I don't even have a good guess about which one it is. Actually, if I'm going to guess, what would you guess it would be?
I'll probably guess the geometric shape came first.
Geometric shape came first, and then the kite?
Yeah.
I'm going to say kite came first, and then the geometric shape. We'll see, though. Anyway, I don't know. All right. Explain 2. So, proving the base angles. Now we're talking about isosceles trapezoids. Okay, we're going to talk about trapezoids first of all. So, a trapezoid is a quadrilateral with at least one pair of parallel sides. Okay, at least one pair of parallel sides. Now, there's different groups of mathematicians define a trapezoid in different ways. Some mathematicians say at least one pair of parallel sides. Some mathematicians say only one pair of parallel sides. Okay? So with at least one pair of parallel sides, as the definition, is a parallelogram a trapezoid? Yes. Okay? But if we say only one pair of parallel sides, then a parallelogram is no longer a trapezoid because it's got two pairs of parallel sides. So it's kind of like up for debate. And I think, let me just hold off here real quick, but I think in the glossary, it might say like a different definition. Let me just check and see here. QRS trapezoid. I could be wrong, but someone told me that they were like, oh, yes. How about that? Wow. Okay, so here's a fun little fact for you. Your book tells you here a trapezoid is a quadrilateral with at least one pair of parallel sides. Okay, ready? And then we go to our glossary in the back, GL38. And we're told that a trapezoid is a quadrilateral with exactly one pair of parallel sides. So, yeah, that's great. Okay, the book doesn't even agree with itself. But we're going to go with this definition for right here, and then we'll forget about the glossary definition for right now. But anyway, how about that? Contradicting itself. So anyway, the parallel sides are called the bases of the trapezoids. So it doesn't have to be on the bottom. It's whichever pair is the parallel side. whichever is the parallel sides, are the bases. And the other two sides are called the legs. Okay, very familiar vocabulary there. Okay. A trapezoid has two pairs of base angles. Each pair consists of the two angles adjacent to one of the bases. So, for example, in this trapezoid right here, this is one pair of base angles right there. That's one pair of base angles. And then there's the other pair of base angles. Okay. This pair is put together because they're adjacent to this base. And this pair, okay, are put together because they're adjacent to this base on top. Okay. And then we talk about an isosceles trapezoid, which again, it's like, well, okay, we've seen the word isosceles before. Isosceles triangle, two sides congruent. An isosceles trapezoid, the legs are congruent. So you can see there in the picture, the legs are congruent. The two bases are opposite each other and parallel there. Well, now that's an interesting look at that. They've marked them as congruent when they are very clearly not congruent there. I think they meant to put probably arrows in there. So there we go. Oh my, this is a hot mess over here. Alright, anyway, so there's that. Okay. And so some properties of isosceles trapezoids. If a quadrilateral is an isosceles trapezoid, then each pair of base angles are congruent. And again, if you go back to the picture here, don't these two angles look congruent? This pair of base angles right here, they look congruent, right? And so do these. Okay, in fact they are, for the isosceles trapezoid. Okay. If a trapezoid has one pair of congruent base angles, then the trapezoid is isosceles. So it kind of like works backwards. If a trapezoid is an isosceles trapezoid, then its base angles are congruent. If base angles are congruent, then the quadrilateral is a trapezoid, isosceles trapezoid. And then if it's a trapezoid to start out with, and it has congruent base angles, it's isosceles. Okay, and then finally, a trapezoid is isosceles if and only if its diagonals are congruent. Okay, so that's another property of isosceles trapezoids. They also have congruent diagonals. Okay. So let's see here. There's some proofs. We don't want to do proofs. So let's go here to explain number 3. We'll do page 475 there at the bottom. Okay, we'll look at this one. And I think then, oh no, we still have the trapezoid mid-segment thing to talk about. Yeah, okay. We'll get to that. Alright, so let's look at this one here. Explain 3. Example 3. Find each measure of value. A railroad bridge has side sections that show isosceles trapezoids. So you can see there's our isosceles trapezoids. Two congruent legs, one pair of parallel sides. The figure ABCD represents one of these sections. AC is 13.2. Okay, so from A to C is 13.2, and BE is 8.4. Find DE. Okay. So AC, what do we call that in this parallelogram here? Since it connects A to C, this is called a what? Oh dear. Let's see here. Oh, Keaton's out. Let's go to Zishan. What do we call AC? A diagonal, right? And so what's true about the diagonals in an isosceles trapezoid? I know, there's lots of properties here. How does it look like they compare? How does it look like AC compares to BD? They're what? They're congruent, yeah. So that means BD is also 13.2. If you know that BE is 8.4, how can we find DE? So from here to here is 8.4. AC, the full length, is 13.2. So that means BD's full length is 13.2. So how can we find DE?
So 13.2 minus 13.2.
Yeah, exactly right. Just subtract them. Okay, we get 4.8. Which doesn't really look right because in the picture there, right, that definitely looks shorter than ED does, but the numbers, they don't lie, so we have to follow the numbers there. 4.8, that's right. Okay, we see that there at the bottom too. Okay. Alright. For B here, asks us to find, on the next page, it asks us to find the value of x so that trapezoid EFGH is isosceles. And I see squares in there. Okay. Lindsay, how can we set this up to guarantee that EFGH is isosceles? What must be true here? If we're gonna make it isosceles, what should be true? Very good. Those base angles, right? This is a base angle, and this is a base angle pair. F and E are base angle pair. G and H are base angle pairs. So that 2x squared plus 21 had better equal 3x squared minus 4 to make an isosceles trapezoid. And then we solved this. So how should we go about doing that, Lindsay?
Would you maybe square root the back square?
So we may take the square root eventually, but right now, let's try and get our like terms together. That's what I recommend we do. Like terms first. So we have 2x squared over on this side of the equation. We have 3x squared over here. So let's try and get those together. What can we do? Yep, and I would have recommended doing that too. I always like to get rid of the smaller of the two. So we're left with 21 here. 3x squared, take away 2x squared is, yeah, just x squared. 1x squared or x squared, even better. Okay, then what here, Lindsay?
You add 4.
Yeah, add 4 to both sides. You get 25 equals x squared. And now what can we do? Yes, now we want a square root, exactly. Okay, so we get x equals, and then because this is an equation, we can say positive 5 or negative 5 here. Either one would work, because when we plug the 5 or the negative 5 back in, they're going to be squared, and they'll make 25 anyway. So, I mean, it's just actually either one of these answers works. Both of those should work. 5 or the negative 5 there. Okay. Yep. 5 or negative 5. So that one worked out very nice. We didn't have to factor or anything. It just gave us a nice little square root. 5 and negative 5. Okay. How about you guys real quick? Take a few minutes. Try 8 and 9. Go ahead, give 8 and 9 a try there. Okay. In both these cases, by the way, folks, that both trapezoids, well, the first one, you're told it's an isosceles trapezoid, and the second one, you're trying to show what value would make an isosceles trapezoid. Yep, values have to be equal. And then here, did you understand what we're saying? Things like your angles and angle R. So this is what. So, you know what to do? Oh, okay. So, same side interior angles. Remember that was like one of the things we talked about way back in our second unit. You have parallel lines, crossed by a transverse line. How should these two angles be related? Right, no. Those are on the same side. Yes. Good. Sure. Okay, good. So here, can you tell me any other angle then? You know, this one's going to be 7. Can you tell me any of the other angles? That's what you're trying to find. That would be something to, because I thought the base angle would be growing. So So it says to use same side interior angle as position. So if you think about it, you're right here, parallel lines, cross by transverse. This angle are the same side interior angle. How are those same side interior angles related? No, they have to be what? Let's do it this way. Let me extend this here to make that transversal hypotenuse. Let me extend this. So like this and this angle are both 77 degrees, right? Because they're corresponding. So it's this one. Okay. But then if you look here, what this angle together with the 77 degree angle takes a straight line. They have to make what? By taking this as a good. Oh. Oh. 22, 4.6. Okay, you did it that way. That's good. That's a good way to think about it. But now, 2x though, right?
Yeah, it's not.
Oh, you didn't write it. Gotcha. Okay. So what did you get? Oh, okay. Okay, sorry. I couldn't read it. I really can't talk because my handwriting is pretty even worse. But okay, there we go. Very good. Okay. Good. So yeah, there are your two answers: 103 and 4. Okay, 103 degrees and 4. All right. By the way, so Hunter and maybe some other people did this too, but you don't have to use the fact that 77 is the same side interior at the 103 here. We can also use the fact that all four of these angles have to add to 360, and so you can say, all right, 2 times 77 plus 2 times that unknown angle equals 360, and then you can solve that way, and you'll also get that x equals 103 that way as well. Okay, because that works. We know that these two base angles have to be congruent and these two have to be congruent, so that's another way to do it. All right. Other questions? We're going to do one more thing and then we'll be done. Okay. We're just kind of picking up some like random little bits here. All right, the last little thing, another little property, and the last little property we're going to worry about is this mid-segment of a trapezoid. Okay, so we have a trapezoid here. Notice it is not an isosceles trapezoid necessarily, it's just a trapezoid. So this works for isosceles and just regular trapezoids as well. And the mid-segment of a trapezoid is very much like the mid-segment of a triangle, okay? It joins the midpoints of the two legs, though. It joins the midpoints of the two legs. And to find the length of the mid-segment of a trapezoid, it's the average of the two bases. So you take BC plus AD, and then just do 1/2 of it, okay? So for example, here in letter A, okay, 12.5 is the measure of one, I'm not on the screen here anymore. 12.5 is the measure of one base, 10.3 is the measure of the other base, so we add those together, multiply by 1/2 or divide by 2, and you get 11.4, so that's going to be 11.4 in length, okay? For letter B here, same idea, but now we have it set up in a different way here. We've got 8.3 is the one base, we have 9.8 is the mid-segment, and we want to find the length of JM. So we have to set up like kind of a bit of an equation here. 9.8 is the mid-segment, and that's equal to 1/2 times 8.3 plus the missing base there, JM. Okay, we have mid-segment, and we have one basis, we need to find the other base. All right, and so to solve this like little equation here, all right, what will we do? Drew, to solve this little equation, how will we solve this to get to x by? Okay, you want to distribute the 1/2? Excuse me. So I get here what? 4.15 equal, plus 1/2 x. Okay, and then what?
Subtract 0.15.
Okay, so subtracting those, we get 5.65. equals 1/2 x, and then what?
Multiply by 2.
Multiply both sides by 2, yeah. And we get x is 11.3. Okay, so that gives us then Jm is 11.3. Okay, so it's just setting up and then plugging in the unknown there. Okay. Any questions on any of that? Okay, so that's just that basic thing. Oof. And then we get to this ultimate Venn diagram here. Okay, so they took the liberty of giving this great graphical organizer of the quadrilaterals, and then from all these you have the rhombus, trapezoid, kite, square, parallelogram, and rectangle. Okay. And so we can kind of fill this in here if you'd like. So this blank right here, what's kind of the big general blank here that we're filling in? Which one of these? So what kind of like which one of these words here contains all of these? I guess if that makes sense. Like what's the big umbrella here we're under? Yeah. Quadrilaterals. That's right. Yeah, the big umbrella here is quadrilaterals. Okay. And then over here, kind of on the side, two distinct pairs of congruent sides. That's what goes there. The kite. Right down there in the corner, kind of off by itself. And then now we go kind of into the groups. So in the groups of quadrilaterals there, the most general is this one. At least one pair of parallel sides. That is the trapezoid. Has at least one pair of parallel sides. At least one pair. And then the parallelogram has how many pairs? 2 pairs. So that's the next one up here. Parallelograms, that's the next kind of like circle in or oval in, I guess I'll say. Okay. What shape has 4 right angles? Square does, but yeah, this is the rectangle in this case, because the square has not only 4 right angles, but has something else. But let's go over here. What has only 4 congruent sides? What shape is that? The rhombus. And then what's the shape that has both 4 right angles and 4 congruent sides? The square. Okay, and so there's our little filled-in Venn diagram. Now with all the quadrilaterals. It's like the little quadrilateral family portrait right there. Okay. And that's it.